Hi, I want to conclude this introduction to Geogebra by looking at a couple of problems where we can apply the functionality offered by Geogebra. The first problem we will look at reads as follows. A plane flies in still air with a speed of 160 miles per hour on a bearing of 60 degrees. The plane then enters a region where the air moves with a speed of 40 miles per hour on a bearing of 120 degrees. The pilot makes no adjustments. What is the resulting speed and direction of travel of the plane relative to the ground? So when you're given a problem, you have to read it carefully, identify the important quantities, and determine the relationship between these quantities. The first thing we have here is the velocity of the plane relative to the air. It's moving at 160 miles per hour on a bearing of 60 degrees. Note that since the air itself is not moving, this is also the velocity of the plane relative to the ground. Next, the plane enters a region where the velocity of the air relative to the ground is 40 miles per hour on a bearing of 120 degrees. Note they don't actually tell you that it's relative to the ground. You need to be able to infer that. So a very important aspect of good reading skill is the ability to infer. So you need to be able to recognize that this is the velocity of the air relative to the ground without them actually telling you so explicitly. The pilot makes no adjustment. So that means then he continues to fly at this velocity relative to the air. But now since the air is moving, this is no longer the velocity of the plane relative to the ground. That is what is being asked for here. So we have identified the quantities and we need the relationship between them now, and that's what we have here. This should look familiar to you. The velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. Let's get some mathematical expressions for the data that we know. We know the velocity of the plane relative to the air, so we can make a vector for that here. Let's use the input bar. So the velocity of the, and I'll just say plane relative to the air. To make something subscript, we have to use the underscore. And if there's going to be more than one character in the subscript, well, then we have to place those characters in curly braces. If it was only one character, then we would not use curly braces. That's the velocity of the plane relative to the air, and that's going to be a velocity whose magnitude is 160, and it's on a bearing of 60, so that's 60 degrees clockwise from north. That means it's 30 degrees counterclockwise from east. So I placed 30 degrees in here, and I did not put the little degree sign, so let's fix that. And there we have it. Remember, Geogebra doesn't create labels with the little arrows on top, so you just need to get used to that. So this is the velocity of the plane relative to the air. Well, this is bearing is 60 degrees. It's 60 degrees from north. Just that to enter the values, the angles in Geogebra, we have to specify it from the positive x direction, counterclockwise. So that's the velocity of the plane relative to the air. We also need the velocity of the air relative to the ground. That has a velocity of 40 miles per hour and a bearing of 120. So a bearing of 120 is somewhere over here. So that's going to be 330 degrees. Notice 120 brings me 30 below here. So counterclockwise from here it's 330. All the way around here is 330. Coming this way it's 120. We can change the zoom a bit. So what we want is the sum of these two vectors. We want the velocity of the plane relative to the ground. So that becomes simply velocity of the plane relative to the ground is equal to the sum of those two velocities. So that's the velocity of the plane relative to the air. Note you have to use the very same variable names that you specified. We add those up and we get this. So we can come over here to our algebra view and see that plane travels relative to the ground with a velocity of 183 miles per hour in a direction of 19.11 degrees. So that's this angle here. So the bearing then would be 90 minus this value here to get this angle over here. Okay, so let's look at another problem. Here's the next problem. You can pause the video and read it. Once again, we have a plane flying in still air, but this time its velocity is 150 miles per hour in a direction 30 degrees north of west. And again it enters a region where the air moves, but this time with a velocity of 25 miles per hour in a direction 15 degrees east of south. Now in this problem, the pilot wants to maintain the same relative velocity with respect to the ground that it had before entering the region of moving air. In other words, before entering that region, this was his velocity relative to both the air and the ground because the air was not moving relative to the ground. In this region, the air is moving relative to the ground, but the pilot wants to maintain this velocity relative to the ground. So the question then becomes, what must then be his velocity relative to the air? So first we analyze the problem and look for the quantities that are important. We then make sure we understand how these quantities are related. The velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. In this problem, we are given the velocity of the plane relative to the ground. That's, we want to maintain this velocity relative to the ground. And we also know the velocity of the air relative to the ground. What we want is the velocity of the plane relative to the air. So we just do some very basic math here, and we see that we can get the velocity of the plane relative to the air by subtracting these two velocities. So let's get our expressions. The velocity of the plane relative to the ground has a magnitude of 150 miles per hour and 30 degrees north of west. So 30 degrees north of west is 150 degrees counterclockwise from east. There we have it. So this is west, and this is 30 degrees north of west. This is north, right? So you're going north. So that's 150 from here. We're also given the velocity of the plane of the air relative to the ground. It has a magnitude of 25, and it's 15 degrees east of south. So this is south, and that's 15 degrees over here. So that's 270 plus 15, which is 285. So that's 15 degrees east of south. So the south, and it's 15 degrees to the east of it. And what I want is the difference between these two. A point that I want to make before I continue is that although we can do this with GeoGebra, and I will be encouraging you to practice using GeoGebra to solve these problems, when you turn in an assignment, you need to do it the way we'll discuss in class and the way it is presented in your notes. I need to see the scalar components. I need to see how you do the math manually. However, you can always use GeoGebra to make sure that your answer is correct, to help you get an idea of what needs to be done. So remember that assignments need to be done showing all your working. GeoGebra is just to help you understand and to make sure you're not making a mistake. So I want the difference between these two vectors. The velocity of the plane relative to the air is going to be equal to the difference between these vectors. So that's the velocity of the plane relative to the ground minus the velocity of the air relative to the ground. Remember, you need to be able to do this using just your calculator. And so that gives us the velocity of the plane relative to the air. So relative to the air, the pilot is going to have to increase the speed to 166.61 miles per hour and change the direction to 143.98. So that's roughly 54 degrees west of north, or 36 degrees north of west. He has to increase the thrust of the engines, and he has to aim a little bit more north in order to travel in this direction relative to the ground. So I hope you're able to follow this. It is a bit abstract, but working with abstractions is one of the objectives of this course. Abstractions are what allow us to work with complexity. So that's it for this video. Actually, for this series of videos that goes along with the notes on vectors. Bye.